up to this point, our discussion about functions in multivariable calculus has been restricted to two types. The first type is a function, say r, which takes in a real number and then outputs a vector. That vector could be in, say, 2 or 3 dimensions. For example, r could describe the path of a particle in space, so that for every time r returns a coordinate x of t, y of t, z of t. So if I'm trying to describe a particle that's moving in space like that, at every time I get a vector which represents the x, y, and z coordinates. And as I move through time, that traces out the curve in space. One example that we saw of this was, say, the unit circle. This would be in 2 dimensions. R of t in that case would be cosine of t, sine of t. Another type of function we looked at is a function that inputs several variables and then outputs a number. Here, a lot of the time, n was either 2 or 3, inputting an x and a y and outputting a number, or maybe inputting an x, y, and a z and outputting a number. For example, we had functions that we could think of as being z equals a function of x and y. This gave us some sort of surface in 3 dimensions. For every point x and y, we could have a corresponding z point, and that would trace out a surface in 3 dimensions. In this case, it looks like maybe a blanket flowing in the wind here. One example we would have of that might be an elliptic paraboloid. And that would be a function z equals x squared plus, say, 2y squared. Now we like to focus our attention on functions that both input and output a vector. These functions we're going to refer to as vector fields. So a function that's a vector field, which inputs one vector and outputs another, okay, will go from the space Rn to Rm. It would input an n-dimensional vector and output an m-dimensional vector. Specifically, we want to look at an example of a vector field defined on a region T in space where f associates with each point x, y, and z a vector, and that vector will often be written as p of x, y, and z, q of x, y, and z, and then r of x, y, and z. So here we're going to input a vector in R3, and then we're also going to output a vector where the first component, p, is a function of x, y, and z. The second component of the vector, q, is a function of x, y, and z. And the third component of the vector, r, is also a function of x, y, and z. Let's look at a simple example in 2 dimensions. we're going to have a vector field f that's a function of x and y, and we're going to let it output the vector x and y. So for example, if we look at f of 0, 0, then that would give you the vector 0, 0. But if you looked at f of 1, 1, the output should be the vector 1, 1. So at that point, we would associate a vector which is horizontally moves 1 unit and vertically moves 1 unit. So it would be that vector there. We could look at the vector, say 1, negative 1. Okay, it's going to move 1 unit to the left and then 1 unit up. And so at 1, negative 1, you would have that vector. At negative 1, negative 1, you would move 1 unit to the left and 1 unit down. So you would get that vector. At 1, negative 1, you would move 1 unit to the right and 1 unit down. So you would have that vector. We could draw in some more vectors. We could draw the f of 2, 1. F of 2, 1 would have a vector that moved across 2 and then up 1. So it would be that vector. We could also do something like f of negative 2, 1. That would move 2 units to the left and then up 1. So that would give you that vector. So I will put in a few more of these vectors so we can see what they look like. Finally, if we wanted maybe to put in the point 2, 2, we would need a vector that moved across 2 and then up 2. So we'd have a longer vector there. So I can put in maybe some longer vectors representing some of the larger x and y values. So for every point, we associate with it a vector field. Let's look at some physical examples of this. So I want to look at one physical example as being Newton's law of gravitation. Newton's law of gravitation states that the force of gravity between two objects is going to be equal to the constants g times the mass of one object times the mass of the other object divided by the magnitude of the distance between them squared, and then multiplied by the unit vector r over absolute value of r. If we're going to look at this, say, in 2 dimensions, okay, then f of r we can think of as negative g m over x squared plus y squared times, and then the unit vector associated with r, which is going to be minus x over the square root of x squared plus y squared, and then minus y. Sorry, those minus signs are already out front, over the square root of x squared plus y squared. Another way I might want to write this is, say, g m over x squared plus y squared to the 3/2 negative x, negative y. So what's interesting about these vectors is that they're all going to point inward. So given a positive value of x and y, then you're going to have a vector that points inward. And given negative values of x and y, you'll have a vector that points in the positive direction. Okay, so these vectors are all going to point inward. What's also interesting about them, this vector field, is that the vectors get longer as you get closer to the origin. Okay, so these vectors, they start off short and then they become longer as you get closer and closer to the origin. And this represents gravity because you think about one of the masses as being located at the origin, and then the strength of the gravitational force is inversely proportional to the distance between the two objects. Okay, so one of the objects is at the origin. So if the other object is closer to the origin, then it'll feel a stronger gravitational force, okay, given by these kind of larger arrows. Okay, and if the object is further away from the origin, the second object in this case, then it'll feel these smaller forces. And so this is the gravitational field that you encounter in physics. And then what you think of is that one of the objects is maybe located at the center. And then you're asking the question, okay, what happens to an object that's under the force of this gravitational field? So an object, say, that's out here in the gravitational field will feel that gravitational force and then be pulled inward to the center. So that's one example of vector fields and how they're used in physics. Another example is something called a velocity field. Okay, we can describe the flow of a fluid, such as wind or water, using a vector field that specifies the velocity at each point. That vector field could depend on x, y, and z, in which case you get a velocity associated with each point x, y, and z. Or I'm going to show you a two-dimensional velocity here, and that depends on just x and y. And so the idea here is that these vectors give you the velocity of, say, some sort of fluid, wind or water. And so then you can kind of trace the influence of that velocity. So you could imagine if you put some sort of dye into this fluid, okay, or some sort of pebble into the fluid, then it would follow the velocity field, and then it would follow essentially the currents of that velocity field. Okay, so I could put a pebble in here and maybe it would follow the currents of this velocity field. Okay, just following the arrows.